So what we're now going to do is put everything together into one curve sketching menu, if you like. So things to look for, we've got to draw some sort of function. We know about points of discontinuity, bottom of the fraction can't equal 0, that sort of thing. So we know to look out for those ideas. They will create asymptotes. So if I had y equals x plus 1 on x, again, bottom of the fraction can't equal 0. So I know y equals x would end up being an asymptote there. Now, on our curve, function x, we now know stationary points. We'll locate those by solving the first derivative equals 0. Once we've found them, we go and classify them. It'll be maximum if it's concave down, minimum if it's concave up, and then it's possibly a point of inflection if it's equal to 0. So then we have to test further to make sure it is a point of inflection. And so what we would need to know is there's a change in concavity. Now, whether you use the third derivative to do that, or whether you test either side of the second derivative in a table, up to you. But you need to show there is some change in concavity if they ask you to find an inflection point. But on that note, if they don't ask you to find inflection points, personally, I don't worry about it. Because it's usually logical whether it's going to change concavity or not. Now, if you've got a minimum point and a maximum point that's continuous, well, it's got to inflect somewhere in between. A curve is increasing, so we know it's going up if the first derivative is greater than 0. Decreasing if it's less than 0. Concave up, second derivative greater than 0. Concave down, less than 0. So we may not need all that information, but they're all the different things we can find if we need to get a better picture of what the graph looks like. So again, we're pretty much stuck with polynomials, so we'll draw this cubic. So let's find our tools. First derivative, second derivative, third derivative. All right, that should be enough. Again, explain what you're doing. Don't just randomly go, oh, let's make this equal to 0, and let people know what you're doing. Stationary points, they occur when the derivative is equal to 0. So in other words, I'm solving this equation. Well, we've got a common factor of 3. That makes life a bit easier. So multiplies together, give 3, adds together, give -4. And we get our answers of x equals 1 or 3. So there are the x values. Let's go classify. When x equals 1, our second derivative is -6. So it's concave down, maximum. Okay, so I know 1, -1 is a maximum. X equals 3, we get a minimum. Now, I said if they didn't ask, I wouldn't bother finding them. I am bother finding them here because, for the sake of the example. So, all right, point inflection, I know that possible points of inflection will occur when the second derivative is 0. Solving that, we get x equals 2. When x equals 2, the third derivative is 6. 6 is not equal to 0. So therefore, there is a change in concavity. So 2, -3 is a point of inflection. That should be enough information to draw a pretty good sketch. So let's plot those points that we found. So 1, -1, 3, -5. The inflection point was 2, -3. Looks like it's just a straight line, but remember we're drawing a curve. X-intercept, they're a bit hard to find on cubics, so I don't think I'll bother. Y-intercept's okay though, -5 down there. So I can draw it in and see how I got away with not finding the x-intercept. Just stop the curve short, draw an arrow. It keeps going. There's a cut there somewhere. So there's my curve. Y equals x cubed minus 6x squared plus 9x minus 5. Now, look, only find x-intercepts if they're easy to find. So obviously any quadratic's easy to find. If you could factorise that cubic, maybe it does, I haven't even bothered to try, but if you could factorise that cubic, then the x-intercepts would be easy to find. All right. Oh, that was a quick one for today, wasn't it?